Welcome back. I did finish uploading. It's 12 noon. So let's try read this too. Oh, that's my airline sim game. So I feel a little tired today. So I think I will stop early making video today. Just go to bed, watch Star Trek.
Zilog Z80. The Zilog Z80 is an 8-bit microprocessor designed by Zilog that played an important role in the evolution of early computing. Software compatible with the Intel 8080, it offered a compelling alternative due to its better integration and increased performance. The Z80 boasted 14 registers compared to the 8080S7, along with additional instructions for bit manipulation, making it a more powerful chip. Initially intended for use in embedded systems like the 8080, the Z80's combination of compatibility, affordability, and superior performance propelled it to widespread adoption in video game systems and home computers during the late 1970s and early 1980s, fueling the personal computing revolution. The Z80 was the brainchild of Federico Fagin, a key figure behind the creation of the Intel 8080. After leaving Intel in 1974, Fagin co-founded Zilog with Ralph Ungerman. The Z80 was released in July 1976. With the revenue from the Z80, the company built its own chip factories. Zilog licensed the Z80 to the US-based Cinetec and Mostec, which had helped them with initial production, as well as to a European second-source manufacturer SGS. The design was also copied by several Japanese, Eastern European and Soviet manufacturers. This won the Z80 acceptance in the world market since large companies like NEC, Toshiba, Sharp, and Hitachi started to manufacture the device, or their own Z80 compatible clones or designs. The Z80 continued to be used in embedded systems for decades after its introduction, with ongoing advancements. The latest addition to the Z80 family is the EZ80, which is offered alongside successor chips. Zilog announced the discontinuation of the Z80 in April 2024 after nearly 5 decades of production. History, edit. Early history, edit. At Fairchild Semiconductor, and later at Intel, physicist and engineer Federico Fagin had been working on fundamental transistor and semiconductor manufacturing technology. He also developed the basic design methodology used for memories and microprocessors at Intel and led the work on the Intel 4004, the Intel 8080 and several other ICs. Masatoshi Shima was the principal logic and transistor-level designer of the 4004 and the 8080 under Fagin's supervision, while Ralph Ungerman was in charge of custom integrated circuit design. In early 1974, Intel viewed their microprocessors not so much as products to be sold on their own but as a way to sell more of their main products, static RAM and ROM. A reorganization placed many of the formerly independent sections under the direction of Les Verdes, further diluting the microprocessor's place in the company. That year, the 1973-1975 recession reached a peak and Intel laid off a number of employees. All of this led to Fagin becoming restless, and he invited Ungerman out for drinks and asked if he would be interested in starting their own company. Ungerman immediately agreed, and as he had less to do at Intel, left in August or September, followed by Fagin, whose last day at Intel was Halloween 1974. When Schimmer heard, he asked to come to the new company as well, but having no actual product design or money, they told him to wait. The newly formed and unnamed company initially began designing a single-chip microcontroller called the 2001. They met with Cinetech to discuss fabrication on their lines, and when Fagin began to understand the costs involved, it became clear that a low-cost product like this would not be able to compete with a design from a company with its own production lines, like Intel. They then began considering a more complex microprocessor instead, initially known as the Super 80, with the main feature being its use of a +5V bus instead of the more common 5+5 and 12V used by designs like the 8080. The new design was intended to be compatible with the 8080, but had many of the nice features of the Motorola 6800, including index registers and improved interrupts. Exxon investment, detailed development begins, edit. While still being set up, the industry newsletter Electronic News heard of them and published a story on the newly formed company. This attracted the attention of Exxon Enterprises, Exxon's high-tech investment arm. At the time, in the midst of the recession, there was very little venture capital available, with a total of $10 million for the entire industry being spent in all of 1975, equivalent to $57 million in 2023. Someone from Exxon contacted the still unnamed company, and arranged a meeting that eventually led to them providing an initial $500,000 funding in June 1975, equivalent to $2.8 million in 2023. With funding being discussed, and a design to be built, Schimmer joined in February 1975. Schimmer immediately set about producing a high-level design, adding several concepts of his own. In particular, he used his experience on NEC mini computers to add the concept of two sets of processor registers so they could quickly respond to interrupts. Ungerman began the development of a series of related controllers and peripheral chips that would complement the design. Through this period, Schimmer developed a legendary reputation for being able to convert logic concepts into physical design in real time. While discussing a proposed feature, he would often interrupt and state how much room that would take on the chip and veto its addition if it was too large. The first pass at the design was complete by April 1975. Schimmer had completed a logic layout by the beginning of May. A second version of the logic design was issued on August the 7th and the bus details by the 16th of September. Tape-out was completed in November and converting the tape into a production mask required 2 more months. Fagin had already started looking for a production partner. By this time, Cinetech and Mostek had both set up the depletion mode production lines that could be used to produce the design. Having talked to Cinetech previously, Fagin approached them first. However, the president of Cinetech demanded that the company be given a second source license, allowing them to sell the design directly. Fagin thought this would mean they could never compete even if they set up their own lines, and the agreement fell through. He then turned to Mostek, who agreed to a term of exclusivity while Zilog got their lines set up, and were eventually given the second source agreement. After considering many names for the new company, and finding them so unmemorable they could not recall them even a day later, Fagin and Ungerman were kicking around ideas based on integrated logic when Ungerman said, "How about Zilog?" Fagin immediately agreed, stating they could say it was the last word in integrated logic. When they met the next day and both immediately recalled it, the company had its name. Into production, edit. The first samples were returned from Mostek on the 9th of March, 1976. By the end of the month, They had also completed an assembler-based development system. Some of the Z80 support and peripheral ICs were under development at this point, and many of them were launched during the following year. Among them were the Z80 CTC, counter-forward/timer, Z80 DMA, direct memory access, Z80 DOT, dual asynchronous receiver transmitter, Z80 SIO, synchronous communication controller, and Z80 PIO, parallel input forward/output. The Z80 was officially launched in July 1976. One of the first customers was a buyer who, unknown to Zilog, worked for NEC. At the time, the Japanese electronics companies were well known for taking US chip designs and producing them without a license. The Zilog team had worried about this, and Fagin had come up with the idea of adding transistors that would be subtly modified to operate differently than a visual inspection would suggest. Shima added 6 of these traps around the design. Sometime later, Shima was told by an engineer within NEC that the traps had delayed their copying efforts by 6 months. The successful launch allowed Fagin and Ungerman to approach Exxon looking for funding to build their own fab. The company agreed, and Zilog built a production line very rapidly. This allowed them to capture about 60 to 70% of the total market for Z80 sales. With their own line running, Mostek was given the go-ahead to start sales of their own versions, the MK3880, which provided a second source for customers which Intel lacked. At the time, a second source was considered extremely important, as a startup like Zilog might go out of business and leave potential customers stranded. Comparison with the 8080, edit. Fagin designed the instruction set to be binary compatible with the 8080 so that most 8080 code, notably the CP/M operating system and Intel's PL/M compiler for 8080, as well as its generated code, would run unmodified on the new Z80 CPU. Masatoshi Shima designed most of the microarchitecture as well as the gate and transistor levels of the Z80 CPU, assisted by a small number of engineers and layout people. CEO Federico Fagin was actually heavily involved in the chip layout work, together with 2 dedicated layout people. According to Fagin, he worked 80 hours a week in order to meet the tight schedule given by the financial investors. The Z80 offered many improvements over the 8080. 1. An enhanced instruction set including 1. A more logical, comprehensible and readable system of assembler instruction mnemonics. 2. More flexible 16-bit data movement, load, or LD, instructions, crucially including the stack pointer SP. 3. More flexible addressing modes for input forward/output to external peripheral ports. 4. Single-bit addressing of all registers and memory, including bit testing. 5. Shifts forward/rotates on memory and registers other than the accumulator. 6. Improved and more accurate than the previous 8080 BCD arithmetic. 7. Rotate instructions for BCD number strings in memory. 8. 16-bit subtraction and 8-bit negation. 9. Program looping. 10. Program counter, PC, relative jumps. 11. Block copy, block input forward/output, I/O, and byte search instructions. 2. An overflow flag with better support for signed 8 and 16-bit arithmetics. 3. New 9 and IY index registers with instructions for direct base and offset addressing. 4. A better interrupt system. 1. A more automatic and general vectorized interrupt system, Mode 2, primarily intended for Zilog's line of counter forward/timers, DMA and communications controllers, as well as a fixed vector interrupt system, Mode 1, for simple systems with minimal hardware, with mode 0 being the 8080 compatible mode. To a non-maskable interrupt, NMI, which can be used to respond to power down situations or other high priority events, and allowing a minimalistic Z80 system to easily implement a two-level interrupt scheme in mode 1. 5. A complete duplicate register file, which could be quickly switched to speed up response to interrupts such as fast asynchronous event handlers or a multitasking dispatcher. Although they were not intended as extra registers for general code, they were nevertheless used that way in some applications. 6. Less hardware required for power supply, clock generation and interface to memory and I/O. 7. Single 5-volt power supply. The 8080 needed 5V, plus 5V, and plus 12V. 8. Single-phase 5-volt clock. The 8080 needed a high amplitude, 9 to 12 volts, non-overlapping two-phase clock. 9. Built-in DRAM refresh, which would otherwise require external circuitry, and less SRAM, more expensive and less dense, but faster, was used. 10. Non-multiplexed buses. The 8080 had state signals multiplexed onto the data bus. 11. A special reset that zeros only the program counter, so that a single Z80 CPU could be used in a development system such as an in-circuit emulator. Success in the market, edit. The Z80 took over from the 8080 and its offspring, the 8085, in the processor market and became one of the most popular and widely used 8-bit CPUs. Some organizations such as British Telecom remained loyal to the 8085 for embedded applications, owing to their familiarity with it and to its on-chip serial interface and interrupt architecture. Likewise, Zenith Data Systems paired the 8085 with the 16-bit Intel 8088 in its first MS-DOS computer, the Zenith Z100. Despite having previous experience with its pioneering Z80-based Heathkit H89 and Zenith Z89 products. However, other computers were made integrating the Z80 with other CPUs. The Radio Shack TRS-80 Model 16 with a Motorola 68000, the December Rainbow with an 8088, and the Commodore 128 with a MOS Technology 8502. Zilog was later producing a low-power Z80 suitable for the growing laptop computer market of the early 1980s. Intel produced a CMOS 8085, ATC85, used in battery-powered portable computers, such as the Kyocera-designed laptop from April 1983, also sold by Tandy, as TRS-80 Model 100, Olivetti, and NEC. In following years, however, CMOS versions of the Z80, from both Zilog and Japanese manufacturers, would dominate this market as well, in products such as the Amstrad NC100, Cambridge Z88 and Tandy's own WP2. Perhaps a key to the initial success of the Z80 was the built-in DRAM refresh, at least in markets such as CP/M and other office and home computers. Most Z80 embedded systems use static RAM that do not need refresh. It may also have been its minimalistic two-level interrupt system, or conversely, its general multi-level daisy chain interrupt system useful in servicing multiple Z80 I/O chips. These features allowed systems to be built with less support hardware and simpler circuit board layouts. However, others claim that its popularity was due to the duplicated registers that allowed fast context switches or more efficient processing of things like floating point math compared to 8-bit CPUs with fewer registers. The Z80 can keep several such numbers internally, using HLHL, DDA and BCBC as 32 bits registers, avoiding having to access them from slower RAM during computation. For the original MOS design, the specified upper clock frequency limit increased successively from the introductory 2.5 MHz, via the well-known 4 MHz, Z80, up to 6 MHz, Z80B, and 8 MHz, Z80H. The MOS version has been produced as a 10 MHz part since the late 1980s. CMOS versions were developed with specified upper frequency limits ranging from 4 MHz up to 20 MHz for the version sold today. The CMOS versions allowed low power standby with internal state retained, having no lower frequency limit. The fully compatible derivatives HD64180/Z180 and Z80 are currently specified for up to 33 MHz and 50 MHz, respectively. Design, edit. Programming model and register set, edit. The programming model and register set of the Z80 are fairly conventional, ultimately based on the register structure of the data point 2200. The Z80 was designed as an extension of the Intel 8080, created by the same engineers, which in turn was an extension of the 8008. The 8008 was basically a CMOS implementation of the TTL-based CPU of the data point 2200. The 2200 design allowed 8-bit registers H and L, high and low, to be paired into a 16-bit address register HL. In the 8080, this pairing was added to the BC and D pairs as well, while HL was generalized to allow use as a 16-bit accumulator, not just an address register. The 8080 also introduced immediate 16-bit data for BC, D, HL, and SP loads. Furthermore, direct 16-bit copying between HL and memory was now possible, using a direct address. The Z80 orthogonalized this further by making all 16-bit register pairs, including 9 and IY, more general purpose, as well as allowing 16-bit copying directly to and from memory for all of these pairs. The 16-bit 9 and IY registers in the Z80 are primarily intended as base address registers, where a particular instruction supplies a constant offset that is added to the previous values. But they are also usable as 16-bit accumulators, among other things. A limitation is that all operand references involving 9 or IY require an extra instruction prefix byte, adding at least 4 clock cycles over the timing of an instruction using HL instead. This sometimes makes using 9 or IY less efficient than a method using only the 8080 model registers. The Z80 also introduced a new signed overflow flag and complemented the fairly simple 16-bit arithmetics of the 8080 with dedicated instructions for signed 16-bit arithmetics. The 8080 compatible registers F, BC, D, HL are duplicated as a separate register file in the Z80, where the processor can quickly, 40 states, the least possible execution time for any Z80 instruction, switch from one bank to the other, a feature useful for speeding up responses to single-level, high-priority interrupts. A similar feature was present in the 2200, but was never implemented at Intel. The dual register set is very useful in the embedded role, as it improves interrupt handling performance, but found widespread use in the personal computer role as an additional set of general registers for complex code like floating point arithmetic or home computer games. The duplicate register file is often referred to as the alternate register set, by some, the primed register file, since the apostrophe character is used to denote them in assembler source code and the Zilog documentation. This emphasizes that only one set is addressable at any time. However, the 8-bit accumulator with its flag register F is bifurcated from the general-purpose register pairs HL, D and BC. This is accomplished with 2 separate instructions used to swap their accessibilities. XFF exchanges only register pair F with F, while the EXX instruction exchanges the three general-purpose register pairs HL, D and BC with their alternates HL, D and BC. Thus the accumulator can interact independently with any of the general-purpose 8-bit registers in the alternate, or primed, register file, or, if HL contains a pointer to memory, some byte there. D and BC can also transfer 8-bit data between memory and accumulator. This can become confusing for programmers because after executing XFF or EXX, what were previously the alternate, primed, registers are now the main registers, and vice versa. The only way for the programmer to tell which set, S, are in context, while playing computer while scrutinizing the assembler source text, or worse, poring over code with a debugger, is to trace where each register swap is made at each point in the program. Obviously, if many jump and calls are made within these code segments, it can quickly become difficult to tell which register file is in context unless carefully commented. Thus it is advisable that exchange instructions be used directly and in short discrete code segments. The Zilog Z80 instruction set includes JAF and JAR instructions which jump to a destination address if the alternate registers are in context, thus officially recognizing this programming complication. Registers, edit. As on the 8080, 8-bit registers are typically paired to provide 16-bit versions. The 8080 compatible registers are 1F, 8-bit accumulator, A, and flag bits, F, carry, 0, minus, parity /overflow, half carry, used for BCD, and an add /subtract flag, usually called N, also for BCD. 2 BC, 16-bit data /address register or 2 8-bit registers. 3 D, 16-bit data /address register or 2 8-bit registers. 4 HL, 16-bit accumulator /address register or 2 8-bit registers. 5 SP, stack pointer, 16 bits. 6 PC, program counter, 16 bits. The new registers introduced with the Z80 are 19, 16-bit index or base register for 8-bit immediate offsets. 2 IY, 16-bit index or base register for 8-bit immediate offsets. 3I, interrupt vector base register, 8 bits. 4R, drum refresh counter, 8 bits, MSB does not count. 5F, alternate, or shadow, accumulator and flags, toggled in and out with XFF. 6 BC, D and HL, alternate, or shadow, registers, toggled in and out with EXX. 7 4 bits of interrupt status and interrupt mode status. The refresh register, R, increments each time the CPU fetches an opcode, or an opcode prefix, which internally executes like a 1-byte instruction, and has no simple relationship with program execution. This has sometimes been used to generate pseudorandom numbers in games, and also in software protection schemes. It has also been employed as a hardware counter in some designs. An example of this is the ZX81, which lets it keep track of character positions on the TV screen by triggering an interrupt at wraparound, by connecting in to a 6. The interrupt vector register, I, is used for the Z80 specific mode 2 interrupts, selected by the M2 instruction. It supplies the high byte of the base address for a 128 entry table of service routine addresses which are selected via an index sent to the CPU during an interrupt acknowledge cycle. This index is simply the low byte part of the pointer to the tabulated indirect address pointing to the service routine. The pointer identifies a particular peripheral chip or peripheral function or event, where the chips are normally connected in a so-called daisy chain for priority resolution. Like the refresh register, this register has also sometimes been used creatively, in interrupt modes 0 and 1, or in a system not using interrupts, it can be used as simply another 8-bit data register. The instructions LDR and LDI affect the Z80 flags register, unlike all the other LD, load, instructions. The sign, bit 7, and 0, bit 6, flags are set according to the data loaded from the refresh or interrupt source registers. For both instructions, the parity /O